Well, good morning, ladies and gentlemen. My name is Neeraj. These are my teammates Tim, Anil, and Nick. And we're proud to present Iris, Vision Beyond Obstruction. We're going to start by telling you about the problem that we sought to answer and how it led to an innovative solution. Next, we're going to talk to you about the design of our system and the mathematical theory or technical background behind our algorithms. Finally, we're going to actually wrap up with a live demonstration of the power and capability of the Iris system. So the problem we sought to address is, how can we maintain surveillance coverage of a subject of interest that becomes occluded? As you can see on the slide, we have a chessboard and Nick covering up a chessboard or occluding the chessboard. Now, with a single camera and single camera surveillance, there's no way that we can do anything about Nick covering the chessboard. We can't see beyond Nick. However, there is a solution, and it's called synthetic aperture imaging. By leveraging some results out of Stanford University, a couple of PhD theses, we've been able to implement a 21-camera array that acts as a discrete approximation of a single camera with a large aperture, a very large aperture. Now, a camera with an enormous aperture has a very narrow depth of field. And the narrow depth of field means that on the plane of focus, any object on the plane of focus is in perfect focus. But any object behind or in front of the plane of focus is blurred out and virtually invisible. And this leads to stunning results, as you can see on our slide. Here, we're able to actually see beyond Nick and focus on the chessboard. So Tim's now going to talk to you a little bit about the design of our system. Tim?
All right, thank you, Neeraj. Now, the system design is absolutely crucial. It's absolutely crucial to our system because without a strong foundation, we will not be able to implement our mathematics. So I'm going to take you through the system design, starting with the camera array, moving to the networked PCs, and ending with the end user interface. So we begin with the cameras, which are now highlighted in red. Now we're using 21 FireWire cameras mounted to an aluminum frame, and it allows for flexible positioning in both the X and the Y direction. And let's talk about the individual cameras. They're all operating at a resolution of 640 by 480 at a full 30 frames per second. And I should also mention we're using grayscale cameras, all fully uncompressed. And this is a picture of our array. Like I said, it's a reconfigurable design, which allows for great flexibility. Now, how do we process all the information from these cameras? I mentioned we have 21 cameras, and they're all uncompressed. That's a lot of bandwidth. In fact, it's on the order of 1.5 gigabits per second. I mean, that's just a tremendous amount of data to be expected to process all in real time. And we overcome these bandwidth hurdles by taking advantage of the symmetric property of our synthetic aperture algorithm. Here you see the breakdown of how we actually arrived to 1.5 gigabits per second. So we take advantage of the symmetric properties, meaning we parallelize both the processing and the bandwidth handling. And this enables for real-time performance, which is quite impressive, which you'll see in the demonstration. But to have such a distributed architecture, we had to build a custom network protocol so all the computers could communicate properly. And we did this a layer above user datagram protocol. And so our system not only allows us to stream video from computer to computer, but it also allows us to communicate the necessary variables to allow our system to act as a coherent unit to form this one single large aperture. And I'll next talk about the end user interface, which is located at the single host PC. Now, we have a product, and with the product comes a professional interface. And this consists of menus that allows you to record. It allows you to calibrate the camera array. It also will allow you to change the focal length all in real time. And I should also mention, the end user is only in control of one computer. The distributed PC network, it could be in a server farm. It's completely removed. As you saw in the overall system diagram, they're all connected via Ethernet. So it really is a robust system, and the end user only has to worry about his one machine. And with that, Anil is now going to talk about the math behind, like what's the magic? What makes all of this work?
Thanks, Tim. The synthetic aperture algorithm has two main phases, homography and calibration. I'll talk about homographies first. What is a homography anyway? It's from projective geometry. It's a transformation from a camera. It takes that image and makes it look like it came from a different perspective. Why do we need them? If we didn't have homographies, the only way we could ever use that array is by overlaying the 21 video feeds. That would be mush. They're all from different perspectives. Nothing would align. Using homographies, however, we create an individual homography matrix for every camera and warp all their video frames to a single virtual position. That way, when we superimpose them, you get alignment like you saw before, and you'll see in the demo as well. But none of this would work if we didn't know exactly where all the cameras were. That's why we have to have a calibration phase as well. We use parallax calibration, which means that we take two different scenes, one with a checkerboard quite close to the array, and one with it a little farther away. In each of the scenes, we find correspondence points over all the cameras, as you can see on the slide. We then measure the displacement of those corresponding points from the close scene to the far scene. And using the parallax property of geometry, we can deduce the exact positions of all the cameras. This is much more accurate than actually taking a measuring tape to the array, and it's a lot easier too, as you can tell. In fact, it's completely generalizable to any camera arrangement, not just some special one that we cooked up. So without further ado, let's do a demonstration and see what Iris can do.
Now, for our demonstrations, we're going to start off with relatively simple situations to give you an idea of just how the system works. We'll then progress to more complex scenarios to show you just what it can do. Now, for this first scenario, Tim is going to stand directly in front of the array. Anil will be behind Tim, and I will be behind Anil. Now, you'll notice on the screen to the left, that is going to be the central camera view. Or we'll put that to the right. Now, the central camera view will be basically blocked completely by Tim. You won't be able to see Anil, and you won't be able to see me. But the synthetic aperture view will be able to focus on Tim, then Anil, and then me, even though I'm occluded by two people. Now, Neeraj is going to sweep through the focal planes and focus on each of us individually.
So we start off focused on Tim, and you can see that the sign he's holding up is in perfect focus. Now, with a normal camera, as you can see, you can't, that's all you get. But with the Iris system, you can actually sweep past Tim and bring Anil into view. You can even sweep past Anil. And there's Nick with holding up his sign. Now, the reconstruction is actually so good that we can actually apply face detection on top of it and find Nick's face through two people.
Now, we're going to increase the complexity of this scenario and bring you to a more practical application. A natural application would be for surveillance in an airport, say. So in that type of situation, you have crowds walking past. Now, for this demonstration, I'm going to be the subject of interest. I'm going to sit down, and Anil and Tim are going to be dynamic occluders. They're going to walk in front of the array back and forth. Keep in mind, in the single camera view, at times I will be completely occluded, blocked by them. You won't be able to see me. But the synthetic aperture will be able to focus on me the entire time.
So as Nick said, we start by focusing on Nick. And you can see that even though there's a crowd in front of him, we're able to see right through the crowd and focus on Nick's face. And once again, we can find his face if we turn on face detection.
We're going to increase the complexity even further. We're going to take this scenario and bring it outside. So what we have here is foliage. You might find this when you're doing... Foliage could use some watering. True.
This is backwards.
Okay.
Yeah.
So you might find this kind of situation with some sort of perimeter security setup. Now, it's important to note that no single camera needs to be able to see me completely. We can still reconstruct the image of my face regardless. So I'm going to again be the subject of interest, sitting here, and Neeraj is going to be able to penetrate through the occlusion and capture my face.
So we start off focused on the foliage, which is way back here. And as we sweep the focal plane, we can get Nick's face, even though he might be blocked in every single camera. And we can superimpose face detection on top of it. Now, not only that, but we can actually, if we turn off face detection, we can actually go beyond Nick and onto the podium. And we're even able to focus there, as you see on the clock.
Okay, now that we've given you an idea of what our system can do, I'd just like to reiterate some of our accomplishments. So first off, we've implemented a calibration scheme which is quick and easy to use. We're also able to develop our own network code, which allowed us to implement a distributed algorithm. And what you see here is a product. This is ready to be deployed. It can be used in the field. It comes complete with a professional graphical user interface, which you saw Neeraj using. Now, we have highlighted the shortcoming of single-camera surveillance. We've also showed that Iris is a compelling solution to that problem. As a result of our strongly distributed algorithm, we're able to adapt to a variety of situations. We hope that you have come to appreciate the power and the capability of our system. We'd be happy to take any questions at this time.
That camera's really not there.
I have a couple of questions. What aperture do you believe would allow you to have a single camera?
I'm sorry, could you repeat the
Could
question?
you get one camera with a sufficient aperture so that you wouldn't need 21?
Okay, so what our system is doing is approximating an aperture that's with the diameter of that size array that you see here. So we would never be able to come close to doing this with one single aperture. We just don't have the technology to produce such.
Okay, and what, that would be an aperture of what, about
2 meters.
3 inches?
Yeah.
What distance will this work over? I mean, if you're trying to do surveillance, probably somebody's going to notice that array, 5 feet away from the person who's surveilled. So what distance do you think would be feasible to have this thing work?
Okay, well, this is all going to be relative to the application. So these cameras could be distributed across a wall, say, and you wouldn't necessarily notice them, and you could potentially have the same number of cameras. You wouldn't have to keep these as dense. So for dense occluders, such as foliage, you want the cameras to be dense, but in that case, you probably wouldn't have to have it so spread out. But in maybe an airport setting, like I think maybe you're getting at, you would want to have it more spread out. You can keep probably the same number of cameras, and you can have it spread out across a wall. Now, what you saw right here, it's all proportional. So we have an aperture of approximately this size, and we were still able to focus on the clock very well. So that's going to scale proportionally.
Oh boy.
Start over here.
Can you talk about some of the uses where you might apply this? More specifically, like have you looked into what kind of surveillance and exactly what would it be doing in the airports? Or does it have military uses, for example?
Sure, I'll address this question. So there are great surveillance applications. One of them is distributing it throughout an airport. And the way you might deploy a system like this is wireless visual sensors. So you can get wireless visual sensors for fairly cheap nowadays, and you can just deploy them, just put them across the wall. You don't need any wires or anything. You can put them in an arbitrary configuration. And as long as you calibrate them and you set up our system, you'll be able to see through occlusions, and you'll be able to see through them far away because you have such a wide aperture. Now, with perimeter and military, sure. I mean, if you have a tighter, you could have a tighter array, more dense. So a smaller aperture but more dense, and you could put that on the back of a Humvee, for example. And you could drive around and you could look through bushes and try to see if there's any activity, suspicious activity behind there. And that might be a great military application. There are also great applications outside of surveillance. For example, because we're able to get such a great focusing on the focal plane but not off of the focal plane, you could use this, for example, to do green screening, where you just focus on a certain plane and then everything else is blurred out. And by using a measure of focus, you can actually discard the pixels that aren't focused. And now you have a green screening effect without actually needing a green screen, which is great for a lot of applications.
I'm sorry, but we're going to have to cut this. Please stick around for questions during lunch.
Sure. We'd love to answer any questions during lunch. We'll be around out there.
Thank you.
Thank you.